Today's lesson focuses on an introduction to chemical kinetics. So kinetics is a fancier term for rates of reaction. And today we'll talk a little bit about how we determine rates of reaction and calculate them. For any chemical reaction that we observe or talk about theoretically, how fast or slow the reaction occurs varies considerably. So some reactions are extremely fast, others are slow, some are medium in terms of their rate or their speed. But either way, the speed or how fast a reaction proceeds is what we call the rate of the reaction. And here's an example of a slow reaction rate. That is the rusting of iron, and that is a very slow reaction. It happens over years. Here is a relatively, quick reaction. So the baking of cookies would be, relatively quick. And then here's a really fast reaction. So when we have the combustion of firework, that reaction is very, very fast. And in chemistry, we see all kinds of varying speeds or varying rates of reactions. So a rate of a chemical reaction is the change in a measurable quantity. This is the key word, always over time, always. And the key word again is measurable. There has to be some aspect of the chemical reaction that we are able to measure. And then we have to represent that rate as a change over time. In order to speed up or slow down rates of reactions, we can alter the reaction using 5 different factors. Now, depending on the reaction, these factors may not always apply, but in any given chemical reaction, one of these factors at least could be applied to adjust the rate of your reaction. So changing temperature, changing the concentration of your reactants, changing the surface area if you had a solid substance, so increasing it or decreasing it. Adding a catalyst is always an option, but you have to know what kind of catalyst applies to your reaction. And actually catalysts are extremely hit and miss. So it's a trial and error in order to understand or determine what kind of catalyst can affect your reaction. And then lastly, nature of reactant. So the nature of the reactant just depends on whether you have, a more reactive substance or something that's not as reactive. So I'm going to give you a little bit of work to do here, and I want you to think about rates of reactions in these 4 scenarios, and how could you change the rate of the reaction. So for the first one, if we think about, the standard magnesium, metal, and hydrochloric acid, what could you do, thinking of those previous 5 factors that would increase the rate of that reaction? For wood burning, think of those 5 factors, which of those would apply and that would allow you to increase the rate of a piece of wood burning? For number 3, how could you slow the browning of an apple? So now what we want to do is we want to slow down the reaction and make it happen very, very slowly. And the browning of an apple, what factors could you affect that would slow that process down? And then just generally, are there any other chemical reactions that we want to slow down? Jot down some answers to this, and then I am happy to check those for you. So when we measure the rate of a chemical reaction, again, we want to know the change in concentration. Now, we use the term concentration in chemistry, but we have to be careful because we automatically think of molar concentration. And you may be able to measure the change in molar concentration, but what we mean here by the term concentration is more of a large or like a looser term, where again, it's just a measurable quantity that you would be able to measure over a certain amount of time. So concentration can be measured a variety of ways, depending on the reaction. So some examples of measuring concentration would be a change in mass, a change in temperature, a change in pH, a change in the volume of a gas produced. And there's other ways, but those would be some, rough examples to measure concentration. So thinking about changes in concentration or changes in measurable quantities, consider these 4 situations and how would you actually measure the rate of the following reactions? So what would be something that you could observe or measure about the actual reaction itself, and that you could measure this, some sort of change over time? So consider Alka-Seltzer with water. The Alka-Seltzer tablet, you place it in water and there's lots of gas that is produced right away. Again, the browning of an apple. How could you measure how fast or slow that reaction was occurring? The souring of milk, the burning of wood. Jot down some answers and I am happy to check those for you. So let's take a look at how we would plot or discuss changes in reaction rates graphically. So here is an example of a reaction occurring, and we see that it's occurring over time, and that kind of follows like with what we see here in the 2 lines that are plotted on this graph. So it's showing both reactants and products over time, and you can tell right away who is who, okay? Here, we're starting at a concentration of 0. This has to be products, okay? We have no products made at time 0. At time 0, we have a bunch of reactants initially. So we know right away that reactants always start off with higher concentrations initially. Products start off with lower concentrations initially. And things that you should notice, right? So here for like the 10 seconds or minutes or whatever it is here that we're measuring, we notice there is quite a drastic change in concentration of both your reactants and products initially. And then as time goes on, the line plateaus and changes very little in concentration. Okay, so we notice that over here with the concentration amount. Over here, this is a similar type of graph. You can tell this is showing products over time. These are questions that I could be asking you, and you can tell it's products over time because, again, we start with none of them. And this is a great little graphic to, again, just show you how the rate is very fast at the start of the reaction. This makes sense. You have lots of reactant molecules initially that are colliding with each other, bumping into each other. They're making products really, really fast. And as time goes on, here are those, look at those little 5 purple molecules in there. They have to find each other and collide and react in order to make products. Well, it's going to slow down. You only have 5 compared to, 100 in that first beaker. This is showing you too how the reaction starts to slow down, it's starting to plateau. And then here, when there's no change in concentration in any way, that reaction has stopped. So what measurement should be used for concentration instead of number of molecules? You might notice that's what they've used in this particular graph. It's not helpful. We cannot measure number of molecules. So we use this graph because it's got a nice image and a nice way to talk about what's happening with the reactants and products. But you cannot directly measure number of molecules. They're too small. So instead, maybe we would like to use mass over time, or volume of gas formed, or pH of a solution over time. There's many different ways that you can measure concentration. Once we have our graph set up and we've plotted the change in concentration over time, we can actually determine rates of reactions as a result. So here again is our graphs here that are showing, again, reactants or products. And then I could say, what is the rate of the reaction from start to finish? And that's what we're showing over here. Here's the start, here's the finish. And what we do is we draw something called a secant. And this is just a straight line that connects 2 points on the graph itself. And then you simply take the slope. Okay, so we know that slope is equal to rise over run, or that's the mathematical way. In chemistry, we wouldn't really say that. We would say, change in concentration over change in time. And you know that you'll take any 2 points on that line and determine the slope to get the rate of your reaction. Similarly, we can also take the instantaneous rate of a reaction as well. And if we're taking instantaneous, what this means is at one particular time. So maybe we want to know the instantaneous rate here at 200 seconds right here. Well, if we ask you to do that, you have to come over to your graph and you have to draw what we call a tangent line. Okay, so the tangent line would sort of hit the 200-second mark, but it also, if you notice, it encompasses a little bit of the curve on either side of the tangent line. This is very, very important that you draw a tangent line that covers as much of the curve on either side of the actual, instantaneous point in time. Then you take your tangent line and you determine the slope of that line. And from there, you can get the rate of your reaction. Here's a graph that you have in your notes. And in your notes, you are asked to determine an average and an instantaneous rate of reaction using the data on this graph. Give that a try and have me come over and check your work. So you can calculate rates of reaction graphically, but you can also calculate them using mole ratios. And here is an example of a chemical reaction where we already know the rate of a reactant or a product. So they're telling us right here that nitrogen dioxide is produced, so this is a product, at a rate of 5.0 times 10 to the negative 6 moles per liter second. That's how you would read that. So they're saying, what is the corresponding rate of disappearance of N2O5? So they're asking us, what would be the rate of that reactant disappearing? So what we're going to do is we're going to set up a mole ratio, and we can use rates in here because rates have a mole unit within them. So we want to know what is the rate of N2O5, and we're going to compare that to the rate of the substance that they gave us. So we know what the rate of NO2 is. And as always, when we're setting up mole ratios, we need to be aware of the molar coefficients. So this rate for N2O5 will be based on the fact that there are, a certain molar coefficient in place. So we're going to say that that will correspond to the moles of N2O5. And whatever the rate of NO2 is, it also corresponds to the actual fixed mole ratio, right, of NO2. So we set this up. So we'll just move along here. So the rate of N2O5 is what I am calculating. I know that the rate of NO2 is 5.0 times 10 to the negative 6 moles per liter second. And then I'm going to equate that to the mole ratio. So N2O5 is 2 moles of N2O5 for every 4 moles of NO2. So I'm going to cross multiply my rate by 2, divide by 4, and then I get a rate value here. So the rate of N2O5 works out to be a negative. Now, be careful with negatives and positives. Negatives here implies that the rate is decreasing because it makes sense. This is a reactant, so the amount is going down. Be mindful of sig figs. So we should have 2.5 times 10 to the negative 6. And again, the unit, moles per liter second. So similarly, we could say, what is the rate of formation of oxygen? And when we set this up, similar to what we just did above, we want to know what is the rate of O2, and then we have to compare the rate of some other substance within the reaction. So we now have 2 rates. We have this original one that they gave us in the question, and now we have this one over here that we just calculated. And I would not use this one that we just calculated in the slight chance that you made an error. Okay, so you shouldn't have, but if you did, then you're not going to calculate the right rate of O2. Let's go back and we're going to set it up using this original data that was given in the question. So we're going to compare this to the rate of NO2, And again, set up mole ratio. So whatever my coefficients for oxygens and my coefficient for NO2s, we're going to apply that. We'll fill in our values now. So we want to know what's the rate of O2. We know the rate of NO2, which was still 5.0 times 10 to the negative 6 mole per liter second. And then those coefficients, I have 1 mole of oxygen for every 4 moles of NO2 produced. So we're going to cross multiply. We're going to divide by 4. The rate of oxygen, rate of oxygen is a positive value because we're producing it, so we're making it over time. But we do have to be mindful of significant figures. And so you should be rounding to 1.3. I need 2 sig figs times 10 to the negative 6 moles per liter second.